Okay, welcome to the last talk of our day. The speaker will be Miguel Abreu from Lisbon, and the title is Fano Bott manifolds and contact invariants of their Gorenstein prequantization.
Okay, thank you very much. I thank the organizers, as all of us do, for keeping inviting me to come to this sequence of conferences. I know it's the 20th anniversary of this conference, but for me it's only the 18th anniversary because the first one I came was in 2007, and I kept coming, and I hope I can celebrate the 20th anniversary, my personal 20th anniversary, 2 years from now. I hope that that is still possible. Okay, so I'll talk about this. Nowadays, you know that these financing agencies have very strict rules about what we have to put on the first page of our presentation. So it's mandatory to put this, okay, with the flag, okay, and the Portuguese Science Foundation and Technology. So, so that's why it is here. It's not like I make a point of this, but since they paid for the trip, fortunately, I'm very happy with that. But then you have to submit the you know. Nowadays things are very funny, right? Yeah, and this is one of those funny things. Anyway, so this is the title. Okay, so let me just say that. Fano, no, it's funny. Fano Bott manifolds are very particular examples of monotone toric symplectic manifolds. Toric symplectic manifolds are very particular examples of symplectic manifolds, and Bott manifolds are very particular examples of toric symplectic manifolds, and Fano Bott manifolds are very, very particular examples of all these things. But they are still at least for me, very interesting, both in the context of contact invariants of their prequantizations, that's what I'll eventually talk today, and also, they also link because they are quite interesting in terms of the existence of extreme calorimetrics, which was a subject of actually the first talk I gave in this sequence of conferences. When I came in 2007, I hadn't started working with Leonardo yet. And so my mathematics was not related to the symplectic dynamics. I worked in, one of the things I worked on was extreme calorimetrics in the context of toric geometry. And these Bott manifolds are actually quite interesting from that point of view, basically because essentially nothing is known about the existence of extreme calorimetrics. I talked about that in a conference in Lisbon 2 weeks ago, celebrating Rui Loja Fernandes, my friend and colleague, 60th birthday. And so I won't talk about that today. I think maybe some other instances. If any of you actually also has a second life interested in extreme calorimetrics, if you know what that is and wants to know why I'm interested, can ask me. I'll be here until the end of the week. Okay, and the plan is to recall what's a toric symplectic manifold, and then explain Fano Bott manifolds as monotone toric symplectic manifolds, and then the contact invariant part. And this contact invariant parts of the Gorenstein prequantizations uses work I did with Leonardo, and at the time when we did the work, a master student in Técnico, Miguel Moreira, who then went to do his PhD at ETH with Raul Pandaripand. Now he's a postdoc at MIT in algebraic geometry. He's not doing symplectic, just symplectic geometry. And also ongoing discussions and work project with Leonardo. And another student, this time a bachelor student, Antonio Neves. And I'll point out what his contributions were in the final year project. This guy is now doing his master's in Amsterdam, but more in computer science. So he's more of combinatorics, and he's a very smart guy. and very helpful for what I'll present. Okay, so what are toric symplectic manifolds? So toric symplectic manifolds are symplectic manifolds, and in the context, at least of the first part, there will be compact symplectic manifolds that are equipped with a Hamiltonian torus action of a torus of half the dimension. So I'm specifying the Hamiltonian torus action as an homomorphism from the torus to the Hamiltonian group. So each S1 factor of this torus generates an S1 action, which has a Hamiltonian function because it's a Hamiltonian torus action. And the set of those n Hamiltonian functions, each of them generating a particular circle action, put together give you the moment map. The moment map is a map from the symplectic manifold of dimension 2n to Rn formed by the n functions that generate the n commuting circle actions. Okay? It turns out that well-known famous theorem, convexity theorem of Atiyah, Gilman, and Sternberg says that the image of this moment map is a convex polytope. It's the convex whole of the fixed point sets of the action that can be described in a way that will be helpful for us as the finite intersection of half spaces. So you have some half hyperplanes, and you decide which half of the half space is determined by this hyperplane is in the polytope, and you intersect all these things, and that's what is this thing. So a polytope is an intersection of half spaces that I'm defining using these equations of this type. Okay. So what is this? This is a linear part plus a real number. These vectors, for each j, this vector is the normal to the half space. And this real number here specifies kind of the distance of the half space with respect to the origin. So if this number is 0, the half space goes through the origin. If it's positive, it's one side. If it's negative, it's on the other side. And my normals will always be inward pointing normals. I'll give several examples of these things. Inward pointing normals. And as I say here, they are integral vectors. That's a condition for this, that follows from these toric things so that the manifold is smooth. Okay, so P is, so the image, more precise I have it here. P is convex, simple, and integral polytope. Simple means that at each vertex you have n edges meeting or n facets meeting, with the normals to those facets being linearly independent and forming an integral basis of the lattice Cn. Integral means this. These guys are in Zn. Anyway, and that's what the Delzham polytope is. Well, I imagine that all of you know what is a Delzham polytope. I'm describing that. I hope you do. If you don't, I have lots of pictures in the talk. Anyway, so here is an important thing, is that these Delzham polytope are a complete invariant of the toric manifolds. This is the theorem of Delzham from 1982. So that's 43 years ago, almost half a century ago, which says they are complete invariants. Okay, so if you have two toric symplectic manifolds that have the same polytope, they are equivariant symplectomorphic. Okay, monotone. What does it mean, monotone? So these things come with the symplectic form, and as all symplectic manifolds, they have a first-term class. Monotone for me will be omega is the first-term class. Okay? Monotone means omega is the first-term class. Not all toric symplectic manifolds can have a symplectic form which is equal to the first-term class, as we'll see in the examples. And that condition of omega being the first-term class, one way of seeing it from the polytope is that the polytope can be described by these same affine linear functions, but all the lambdas can be taken to be 1. Meaning that all the facets are at an integral distance 1 to the origin, as we'll see from the examples. Okay? It's toric geometry. So you can pick this one. This one will appear again later on. Okay? So let's see some examples. Well, every talk that has, I think every talk I've given in my life, and I think I already said this probably, you guys heard me this. I give talks since, I don't know, 30 years ago, maybe more. I think every talk I've given in my life, S2 appears. It appeared when I dealt with symplectomorphism groups. It appeared on Cayley geometry. So it has a very nice extremal metric, the round metric. It's a toric manifold. So I think for me, anything that I work in mathematics, if it doesn't apply to S2, I'm not going to work on it. So I only work on things that apply to S2. And that is actually the first example. So here is a toric manifold, S2 with its standard area form. And okay, the S1 action is the rotations that you see here in the picture. The moment map is projection. And it's monotone exactly when it has radius 1, up to suitable normalizations. But that's the one. Okay? And so the facets of this polytope, here is a moment polytope. What are the hyperplanes are these 2 points in this case. And the facets you see that you express at minus x plus 1 and x plus 1. So that's the two inequalities that define this polytope. And so this is an example of a monotone. A second example, class of examples in this case, not all of them are monotone, are Hilsbrook surfaces. These will be, so essentially, as you will see, Bott manifolds generalize Hilsbrook surfaces. Hilsbrook surfaces are 4-dimensional manifolds obtained as S2 bundles over S2. See, S2 is everywhere. S2 bundles over S2 or P1 bundles over S2. And how do you obtain an S2 bundle over S2? Well, you take a line bundle, which is determined by a first Chern class, and then you projectivize the line bundle. What does that mean? You add a trivial bundle, complex line bundle to this. So this is now a 2-dimensional complex vector bundle. And then you projectivize each one. Okay? So everything is determined by the Chern class of this line bundle. So that's an integer. That's this number k. Okay. And a Hilsbrook surface, any k, you can use any k, positive or negative. There are then some isomorphism between these two things. And so the polytope, up to those lambdas that I'll discuss later, but the polytope that gives the toric structure of this Hilsbrook surface, note that you have a two torus acting, because you have an S1 acting on S2, this action lifts to the total space, and then you have the action on the fibers. So you have two commuting torus circle actions. So that's a 4-dimensional manifold with a two torus action. It's a toric manifold. The polytopes that arise are like this, and the normals, the ones I'm drawing here, and the normals, where does the k enter? The normals are, I can normalize so that the normals to the facets are the canonical basis vectors, 1, 0, this one, 0, 1, this one. And then the other one you can take to be 0, minus 1. And then only this one, which is minus 1k, actually, if I draw it to scale, it's something more like that. If k, for this guy, it's something, the normal is like this, minus 1k. Up. So this normal, which I'm drawing here, specifies this slope. And then, depending on where this facet is moving with respect to the, or also where this is up or down, that specifies the size of the symplectic form you are taking. Okay. So, but in terms of normals, these Hilsbrook surfaces, I can write the normals in a matrix, put them as columns of a matrix of this form. Here I have the identity matrix, which give you the 1, 0 and the 0, 1. 1, 0, 0, 1. And then I put the other two normals in this way. The minus 1k I put here, and then the 0, minus 1 I put here. And so this gives me a lower triangular matrix whose columns are the normals to this polytope, and where the k appears here. Okay, because this is, you'll see a generalization of this in high dimensions. Okay. Note another thing is that it is well known that as smooth manifolds, these Hilsbrook surfaces are diffeomorphic to S2 cross S2, the trivial S2 cross S2, when k is even. The bundle is, when k is 0, the bundle is trivial. But when k is 2 or k is 4 or k is 6, the bundle is non-trivial. But the total space is still diffeomorphic to S2 cross S2. And are diffeomorphic to the non-trivial S2 bundle over S2 when k is odd. Okay, these are well-known things about these things. Okay, so this means, for example, that S2 cross S2 as a smooth manifold has several different inequivalent toric structures. There are different torus actions, one for each even number k, specified by this polytope, for example. Okay? The same manifold can have several torus actions in the same symphony. Okay. What are the monotone toric symplectic four manifolds? So what are the monotone Delzham polytopes, or polytopes which can be expressed with that last coordinate, this lambda is equal to 1? They are well known to be these 5 guys here. Only 5. Okay? So this is the polytope that gives P2, or CP2, projective space. And then you can blow up it once, which means you chop this corner here. I'm not saying what that means, but that's once. You can blow up twice. You chop this corner, and you get this guy. And you can blow up 3 times, and you chop this corner, and then you get this guy. Or you also have the trivial P1 cross P1. These are the 5, only 5 Delzham polytopes that correspond to monotone toric symplectic manifolds. C1 is equal to omega. Note that the only 2 Hirzebruch surfaces that you see here is the trivial one, P1 bundle over P1, the one that is determined using this matrix here of normals by the minus the identity matrix. So there, the Chern class is 0 of the bundle, so you get trivial P1 over P1, so S2 cross S2 with its standard action. And the first Hirzebruch surface with K odd, K is equal to 1. Okay? Those are the only 2 monotone Hirzebruch surfaces, meaning the following. As a smooth manifold, S2 cross S2 has only 1 monotone toric structure. It has infinitely many toric structures, but only 1 is monotone. And the non-trivial S2 bundle over S2 has only 1 monotone toric structure. Again, it has infinitely many toric structures, 1 for each K odd, but only 1 of them is monotone, admits a symplectic form whose cohomology class is the same class as the first Chern class. Okay? Are we good? So let's go to Fano Bott manifolds as monotone toric symplectic manifolds. So Bott manifolds were introduced by Grossberg and Carchon in 94, in the paper published in 1994. And they discuss them, they arise in something related with some representation theory of the groups, and the story of how they appeared has several nuances, but I'm not, I don't even know why they are called Bott, because there were some Bott Samuelson manifolds, and then Grossberg and Carchon called them Bott towers and Bott manifolds, and so that's became like that. Bott manifolds. The Bott is for Raoul Bott. It's not any other Bott. It's Raoul Bott. Okay, and so what are they? They are iterated P1 bundles, iterated S2 bundles. So you start with a point, take an S2 bundle over a point, that's S2. Then take an S2 bundle over S2. That's a Hirzebruch surface. Then take an S2 bundle over this guy. Now you have more choices of Chern classes. Take an S2 bundle. All S2 bundles are always constructed in the same way. You take a complex line bundle over the previous lower dimensional Bott manifold, take a complex line bundle, add a trivial one, and projectivize. So everything is determined by the Chern class of this complex line bundle, up to equivalence. Okay? So it's not difficult to think as toric symplectic manifolds. They are determined by polytopes whose normals are the columns of a matrix of the following form. And let me tell you how do you see this. So the form is the following. I'm going to, the columns of this matrix are the normals. I can always normalize one vertex of a polytope so that the facets at that vertex are the coordinate planes. And hence the normals at that vertex are the canonical basis vectors. So these are these columns here, right? These are the canonical basis vectors of our N. That makes the identity matrix. So that's I normalize. So that means that I went here to this corner, and I normalize these two guys. 1, 0, 0, 1. And then you have another n normals, which are kind of defining now the opposite facets to these things, because the polytopes of these iterated Bott manifolds are like combinatorial versions of the cube, of the hypercube, think of cubes, okay? Like here you have the square, that's the trivial one, and then this is combinatorially equivalent to the square. It has opposite facets, they are just not orthogonal opposite facets. And the same happens in higher dimensions. So now you have, for each of these normals, you have another normal which is defining kind of the opposite facet, starts with the -1, so for this one you have a normal with a -1, and then another one with a -1 on these diagonals. And then you have a bunch of numbers here, lower triangular matrix. And how do you see these line bundles, these line bundles, the Chern classes of these iterated line bundles? You see, this number here is specifying the Chern class of the first line bundle, first non-trivial line bundle. It's a line bundle over P1 that's determined by a number, one number. That's the Chern class, that's this number. Then you go to the second stage, and now you have a line bundle over kind of P1 cross P1. So it's determined by two numbers, the Chern class. Those are these two numbers. So that's why I'm saying that these two numbers specify the first Chern class of the next line bundle. And then you have, okay, and then this is, I think, I hope it's self-explanatory. So as you have more and more factors, the Chern class of a line bundle needs more and more numbers. The rank of the second cohomology of a manifold is growing by 1, so you have more numbers, more numbers, more numbers, and that's it. And these are the numbers. Okay? These at least, I think, so everything is determined by a lower triangular matrix of this form. This part is the identity. I kind of canonically normalized one vertex to have standard feature, and then you have another guys. So lower triangular matrix with integer entries here. That's how it is. Okay. And then it's curious because I didn't look for everything that has been written with the name Bott manifolds on it. So, but after this paper that introduced them, suddenly, starting in 2019, that's only 6 years ago, and then results appeared about these Fano Bott manifolds. So, for example, so these numbers a priori can be any integers. Any integers that you put here will give you some Bott manifold. It might not be Fano. You see, for Hillsbrook surfaces, you can put any k here. But the only Bott Fano ones were k equals 0 and k equals 1. Only two of them. Okay. The same thing happens in general. Any integer that you put here will give you some Bott manifold. But if you are looking at Fano ones, which I am, for reasons that you will also see in a minute, then these numbers have to satisfy some very specific and rigid relations. And this guy was the first guy to clearly list those conditions in a complete and correct way, which is this Japanese mathematician, Suiyama, 2019, and he says, here are some rules. You know, I'll say a bit about these rules, but who cares, right? There are some rules that say, you know, some of these matrices give you a Fano Bott manifold, others don't. And the rules are all specified in terms of the columns. For example, the first rule says, one possibility is all the numbers in a column are 0. That's good. The second rule says, all the numbers in a column are all zeros except 1, which is 1. All zeros except 1, which is 1. So you might have everything 0 below the diagonal, below the -1, or just have 1, 1, and everything else 0. Or, if you have a -1, so suppose, let me just tell you what are the rules so that you see how rigid they are. Suppose you have this guy, say this guy, I like this guy. Suppose this guy was equal to -1. Then, you go to the column that has that -1 in that level in the diagonal, And then these guys here have to be the same as these guys here. Then they have to repeat. And the other rules also apply. Okay? So it's extremely rigid. Anyway, he completely characterized the ones that correspond to Fano Bott manifolds. Okay? Very rigid.
And no condition above?
Well, the rest applies. For example, it can be all zeros, or you might have 1, 1. Sorry. No. I'm lying. Everything above the minus 1 is 0. I'm lying. Could be anything. Wait, could be anything if it's equal to this. But these now, what are the rules for this? It's either zeros, or just a 1, or if it has a minus 1, then it has to apply to this. Okay? Very good. And then, 3 years later, another 2 Japanese mathematicians, Higashitani and Kurimoto, told you when 2 matrices give you the same Bott toric manifold. Because there are different ways of obtaining, you can change bases, you can permute and things like that. And so they kind of gave rules. And while in the process of telling when one of those lower triangular matrices give an equivalent Bott manifold to another one, using certain operations that I'm not going to specify, but the most important thing they said is the following. That 2 Bott manifolds, and in this case they were not even dealing with Fano Bott manifolds, only 2 Bott manifolds are diffeomorphic if and only if their cohomology rings are isomorphic as radial rings. So the cohomology rings determine the diffeomorphism class. Okay? So that's these cohomological rigidity results that you are looking. So actually, there is a conjecture that says that this is true for any toric manifold. There is a conjecture that says this is true for any toric manifold. But it's unknown. But these guys proved this for this I'm going to emphasize this again because I don't want you to think that this is a very, very big thing. It's not. Very special class within the very special class of toric manifolds. But anyway, but there is a conjecture that says that for any 2 toric manifolds are diffeomorphic if and only if their cohomology rings are isomorphic as graded rings. Okay? And moreover, there is even a strong thing that says any isomorphism, graded isomorphism between these rings should be able to be realized by a diffeomorphism of the corresponding toric manifold. But that is unknown. But that is true for Bott manifolds. And actually, let me point out, because it will be important in the sequel, is the following. So the simplest model of a Bott manifold is the Cartesian product of S2s. Trivial bundle, trivial bundle, trivial bundle, trivial bundle, trivial bundle. And just as abelian group, so the rank of the cohomology of any Bott manifold of dimension 2n is the same as the rank of the cohomology groups of S2 cross Cartesian product of S2. So the rank of H2k is n choose k. Okay, because that's what happened for the Cartesian product of S2. So the rank, the odd dimensional cohomology as happens for any toric manifold is 0, and the even dimension cohomology has rank n choose k. So the thing is that the ring structure is different. Right? So they are all distinguished just by the ring structure in the cohomology. And then you might ask, so if they are diffeomorphic, if and only if the cohomology rings are isomorphic, then you say, okay, come on. At least for me, when I was starting to read these things, I thought, how difficult it is. I give you 2, cohomologies with some rank. Yes, this is for any given 2 Bott manifolds, the following are equivalent. Yeah. Not Fano, necessarily. No, they are not. I'm not saying. I'm saying that as abelian groups, the cohomology groups have the same rank. Yes, for any Bott manifold.
So wait, so CPN is not like...
No, CPN is not a Bott manifold.
It's not like you take one, then you take...
CPN is not a Bott manifold. CPN is not an iterated P1 bundle over P1. Bott manifolds are S2 bundles over sequences of S2 bundles, P1 bundles.
Sorry. It's kind of like the generating of
Yeah.
the things of
Yes. Okay, but so the thing is, when I was reading this, I thought, because algebra was always a very bad thing for me, even in, that was the design. When I went to Stanford, the first year at Stanford, you have to do the quals. And the quals are real analysis, complex analysis, and algebra. And algebra, I thought, it's a 6-hour exam, right? 3 hours in the morning, 3 hours in the afternoon. It's terrible. Very, very bad for me. Anyway, and so I thought, look, I look at this. Come on, I give you a cohomology group. I give you groups, a billion groups, all of rank n choose k. Then put some ring structure there. How many ring structures can you put in? If you give me 2 ring structures, I'll tell you right away if they are isomorphic or not. Actually, this is a completely non-trivial problem that people took a long time. In general, it's very difficult to solve. And even in the context of these Bott manifolds, it required 2 more papers by these guys, Showley, Massoud, and Park, that first of all, they proved 2 very nice things, actually. They proved that they improved this diffeomorphism thing for Fano. Now, for Fano Bott manifolds, if they are diffeomorphic, then they are equivalently diffeomorphic. Meaning that what we see for Fano Bott manifolds in dimension 4, meaning only one toric structure on each diffeomorphism class, happens in higher dimensions also. Okay? Only one Bott toric structure on each diffeomorphism class. And they were able to classify the cohomology rings that appear, to enumerate the cohomology rings that appear, using some combinatorials and invariants of the cohomology rings. Okay? And here is the table they constructed. So I decided to write, I said it's a very special class of toric manifolds. So I decided to write, so people have been enumerating Fano toric manifolds in general. And for example, Aubry, in his thesis of 2007, provided an algorithm that was able to say that the number of Fano toric manifolds in each dimension up to dimension n equals 8, so dimension 16. Here are those numbers, so 18, for example. So 5, the 5 in dimension 2 are the 5 ones I made the picture. Then there are 18 in dimension 3, 124, and so forth. So you can read the numbers. I also got this one now. So it's special, but there are several thousands of them. And the Bott ones, the Fano Bott ones, here they are these numbers that these guys were able to provide. Okay, for example, in dimension 3, there are 5. So here are the 5 ones in dimension 3. So there is P1 cross P1 cross P1, determined by these 3 normals here, the cube. And then I'm just drawing, there is P1 cross the first Hilsbrook surface, that's a Fano one, here it is also. You can see the first Hilsbrook surface cross P1. Then there is this bundle with Chern class 1 minus 1 over P1 cross P1. Here it is the polytope. Chern class 1, 1. Here it is the polytope, and here are the matrix satisfying those rules. And then there is the more non-trivial one, is the one where you take the first Hilsbrook surface, which is a non-trivial S2 bundle over S2, and then you take another non-trivial S2 bundle over S2. Note that these ones are all, the first level is trivial, and then you put something non-trivial. First level is trivial, then something non-trivial. Then here, it's kind of a Cartesian product of previous ones. This is the one where you have something non-trivial and then something non-trivial. So you have 2 columns with ones. So these are the 5 that you can classify. And then in the next dimension, there are 13, and the algorithm gives you a way of enumerating them. I only did this exercise for n equals 3, and you can do more. Okay, so this is what I wanted to say about Fano Bott manifolds. Very specific. One diffeomorphism class and one toric structure associated to each diffeomorphism class, and you can enumerate them. Okay. Now, contact invariants of their Gorenstein prequantization. What are Gorenstein toric contact manifolds? So these are the contact geometry analog of symplectic toric manifolds. And Gorenstein just means, it's a fancy name, but it's one that's used in algebraic geometry, for C1 is equal to 0. So these are the ones that have the contact structure has first term class 0. So, but one way of defining them is through the symplectization. The symplectization of a contact manifold is a symplectic manifold, and you can ask it to be toric, with a torus action that commutes with the R action that comes from the symplectization. And so, if you think of that, that means that the moment map will be a cone. Essentially a cone over a polytope. Okay? So they can all be constructed as contact reductions of the standard contact structure on the odd-dimensional sphere. So they are all quotients of the standard contact structure of the odd-dimensional sphere. The ones I'm interested in, which are called good contact toric manifolds. And so their moment polytopes, in this case, are cones, so all the facets go through the origin. Think of a cone, a polyhedral cone. It's determined by hyperplane facets that go through the origin. So those lambdas are all 0, those numbers. So you just need to specify the normals to the facets. So they are determined by the normals to the facets. Okay? So the cones are determined by the normals to the facets. Okay? These are the ones I call nu J. And the moment cone of the toric contact manifold, it's the image of the moment map of the action of the torus in the symplectization. It's this guy. Gorenstein means that the first term class is 0, as I said. And this, in terms of the normals, has a non-invariant description, but it's the one very useful. Means that up to a change of basis, you can assume that the last coordinate of the normals of the cone is 1. The normals lie on an hyperplane. The normals itself lie on an hyperplane with last coordinate 1. So what you need is to specify the first n coordinates of each normal, and then put the 1 in the end, satisfying the answer. Okay? And so look at this now. So you are taking, right, my dimension, I'm being too fast because I talk too much and I'm looking at the clock and it's stressing me. So anyway, the contact manifold has dimension 2n plus 1. Okay? That's my normalization. So the symplectization has dimension 2n plus 2. So meaning that the torus action that makes it toric is a n plus 1 torus. So the moment map goes to Rn plus 1. So the cone is in Rn plus 1. So these normals have n plus 1 coordinates. The last one is 1. So these guys are n coordinates here. So these guys here are vectors in Rn. Again, these guys here, which are the normals to the cones, are vectors in Rn, integral vectors in Rn. So, and the smoothness, a cone with these normals gives a smooth toric contact manifold if and only if the gadget that you obtain as the convex hull of these vectors, which are the first, it's what's called a toric diagram. It's a simplicial polytope. Okay? All facets are simplices and are unimodular simplices. All facets are simplices and are unimodular simps. Look at this. What I'm doing here is the convex hull of the normals. So I'm going to draw lots of pictures now. Because don't think of moment polytope anymore. It's the dual of the moment polytope. You are taking the normals and taking the convex hull of the normals. Meaning the normals of the moment map, which becomes the vertices of this toric diagram. Okay. So I'm using the notation to a toric diagram. I can construct by symplectic reduction from the standard contact structure on the sphere a toric contact manifold, and the same thing, the Lerman theorem and the analog of the Alsdon theorem in this context states that these contact toric manifolds are determined by these toric diagrams. Main examples for today. Prequantizations of monotone toric symplectic manifolds. If you have, and forget toric, if you have a monotone symplectic manifold, you can take the symplectic form is integral, you take a line bundle whose first Chern class is the cohomology class of the symplectic form, which is equal to the Chern class of the base manifold, and this is a contact manifold called the prequantization, right? And it turns out that this exactly produces always contact structures with C1 is equal to 0, because you are taking the cohomology class of the symplectic form is the same as the first term class of the base, and so C1 is going to be 0 upstairs. It's skilled in this. Okay, so prequantizations of monotone toric symplectic manifolds. So, in particular, look what is the toric diagram. It's kind of the construction. See, this one, if you take a monotone toric symplectic manifold, the polytope has this one. Remember? Now, take the cone. You see, I should have drawn here. You see, you have a polytope. Let me draw, make here a drawing, which is the following. Take a monotone, first of all, P1, which has its moment polytope is this simplex. Okay? Now, take the simplex, what is the prequantization, what is the cone corresponding to the prequantization of this thing? You put this segment at level 1 in one more dimension and take the cone over it. Okay? What are the normals to this cone? What are the coordinates of the normals to this cone? It's this vector and this vector. This vector has coordinate what? What? 1, 1. And this vector has coordinate minus 1, 1. This one and this one are the ones that came from the facets below, are these ones. And this one and this minus 1 are the normals here. Okay? So, when you take a prequantization of a monotone toric symplectic manifold, the normals of the polytope become these pieces here. The normals of the polytope become these pieces. So the toric diagram is the convex hull of the normals of the polytope. So the toric diagram has vertices, the normals of the polytope that you just prequantized. Okay. So I'm saying the toric diagram is, that's called the dual polytope. Okay. So let's take here examples of toric diagrams. So if you do the prequantization of the monotone S2 cross S2, its moment polytope is the square. The normals to the square are the vectors 1, 0. This guy has coordinate 1, 0. I can write this actually. This normal 1, 0. This guy 1, 0. This normal 0, 1. This guy 0, 1. You get the picture? Okay? And then you take. So this is the toric diagram of the prequantization of the monotone S2 cross S2. And this is a toric diagram of the prequantization of the other monotone Bott manifold in dimension 2, which was the first Giesbrook surface. Okay? Here it is again. Just this. Okay. In n equals 3, remember there were 5 monotone Bott manifolds. They all admit prequantizations. Here are the toric diagrams, are the duals of this. So cube, moment polytope of the base, toric diagram of the prequantization. Polytope of the base, toric diagram of the prequantization. Anyway, so this guy is the convex hull of the normals of this guy. In the other way, by the way, this guy is the convex hull of the normals of this guy. That's how things work. So here are the 5 examples that you have. Okay, now, contact invariance of the prequantization. So I've talked about this, I think, for several already, sometime in this conference, so I would assume you will know. Anyway, so for these toric contact manifolds, so one of the way we started working together, me and Leonardo, was figuring out that you can use toric geometry to compute the contact homology, the simplest contact homology of these toric contact manifolds, because you can use explicit Reb flows that look like irrational ellipsoids. You take an irrational vector in the Lie algebra of the torus acting, and you know exactly what is its flow, where are its closed orbits, finitely many, and its iterates. You can compute the indices using the fact that these are quotients from the sphere, and you compute everything. All indices have even dimension. The SFT index have even dimension, so the boundary map in the complex is 0. So you are essentially counting how many orbits of each degree do you have. And that gives you the rank of the contact homology of this map. Okay? So, I define, so given a toric diagram, I have a toric contact manifold. I told you I can compute contact homology, and I'm telling you, I'm saying the contact Betti number of a toric diagram is the rank of the contact homology in degree k of the corresponding toric contact manifold. Okay? So, as I said, all orbits have even degree, so the rank in odd degree is 0. There is no contact homology in odd degree. And then, much later, in that work with Miguel Moreira I mentioned, we found a combinatorial way of describing the ranks of the other, of the even dimensional contact homology. And in a nutshell, it says the following. The toric diagram has all the information through its Erhard polynomial. What's the Erhard polynomial of an integral polytope in general? The Erhard polynomial is a polynomial obtained as you count integer points inside the polytope, and it's scalar. So the Erhard polynomial, the fact that it's a polynomial is a theorem, but it's the Erhard function of a polytope is a function that counts the number of, well, this is the same thing as the number of integral points. So you multiply your toric diagram by t and you intersect with Zn. That's the same thing. You count the number of integral points inside the polytope and its scalings. Okay? And then there is a theorem. This is a well-known thing in combinatorics, this Erhard polynomial. And there are some theorem about its coefficients and about its nature. In particular, if you write the polynomial in a polynomial basis given by this type of polynomials, here, forget about that, the coefficients are all non-negative, integer non-negative coefficients. And the theorem that we proved appeared in 2023, but actually the theorem that I think it's from 2018 or something, was that these numbers, which are the coefficients of the Erhard polynomial, which is a completely combinatorial Gaussian, tell you the rank of the contact homology. Say, the rank starts at 0, and it grows every time you have a coefficient, non-zero coefficient. Okay? So, the message is, the Erhard polynomial tells you exactly what is the contact homology, the ranks of the contact homology group of a toric. So, it's a completely combinatorial thing. So, for example, our result says, well, the rank, for example, the rank of the 2K, the contact Betti numbers, for example, for the toric manifolds, stabilize at a particular value given by n factorial times the volume of the toric diagram. So the mean order characteristic is given by the volume of the toric diagram. Then the first one that is below the stabilization range, which starts at 2n, is n factorial, it's the volume minus 1. And then, for example, the zeros Betti number is the number of integral points inside the toric diagram, in the interior of the toric diagram. Anyway, there are, I have discussed this in the past, but now look, note the following thing. Now let's get back to these Fano Bott manifolds. Remember that, so I'm now looking at the prequantizations of these Fano Bott manifolds. These Fano Bott manifolds, the rank of the homology of the base is the same for all of them. They all look like, from this point of view, S2 cross S2 cross S2. They have the homology of the base has the same rank. And in this setting of very smooth things and monotone things, you can quote Bourgeois' theorem that says that the contact homology can be obtained in these prequantizations by a sum of the homology of the base by shifts. Okay? Everything is determined by the rank of the homology of the base. But the rank of the homology of the base is the same for all Bott manifolds. So that means that the contact Betti numbers are the same for all these prequantizations. So this says that the Erhard polynomial of all these toric diagrams is the same. Okay? So a corollary is the toric diagrams obtained as dual polytopes of the monotone polytopes obtained from Bott manifolds provide a family of polytopes that are Erhard equivalent to what's known as the cross polytope, which is the toric diagram of the Cartesian product of S2s. This is the cross polytope. So it says, for example, here the following. This guy is the simple guy. The cross polytope is very well known also in combinatorics. It's the dual of the cube. All these other polytopes have the same Erhard polynomial. So this guy has the same number of integer points inside as this guy, and if you scale, also the same thing. Has the same Erhard polynomial. And you get that because by looking at, the contact homology is the same, and so they have to be the same. Anyway, and you can specify. So in particular, so this was the motivation, because I asked, one of the things we were discussing was, I'll ask some questions very soon, with Leonardo, and then I asked António Neves in his bachelor's thesis to help me, because he liked combinatorics a lot and he liked to do these things, is how do we obtain, given a toric diagram, so in the, how do I obtain other toric diagrams that have the same RR polynomial? What kind of constructions can I obtain? Are there any or not? And so, and he found a very efficient way of producing potentially toric diagrams RR equivalent to a particular given one, given by what's called a bipyramid construction. In particular, when applied to this setting of these cross polytopes and this setting of Bott manifolds, he found a very good algorithm to enumerate all the distinct toric diagrams that are R equivalent to the cross polytope. And you see, there were these numbers of those in this case, Korean and one Japanese and 3 Korean mathematicians who told how many Bott manifolds were in each dimension. Okay, and António Neves enumerating the number of toric diagrams that are RR equivalent, or that have the same RR polynomial to the cross polytope, recovered these numbers, and because his algorithm is much better, was able to run in his laptop the thing for up to n equals to 15. So for example, for n equals to 15, there are 6 million Fano Bott manifolds, inequivalent ones. Okay? So this is a very particular class, as I said, very particular class. Within a very particular class, but still, at n equals 15, there are 6 million of them. See, for me, that's infinity. I know it's finite, but come on. What can you say about 6 million manifolds? But all these 6 million manifolds, their prequantizations, you see, these are all non-diffeomorphic manifolds. They are not just non-toric equivalent manifolds. There are 6 million diffeomorphism classes of Fano Bott manifolds. Remember that for Fano Bott manifolds, being different means being diffeomorphically different. You see, at n equals 2, this number 2. S2 cross S2, non-trivial S2 bundle over S2. This number 5, it's 5 different diffeomorphism classes. Also toric manifolds, but 5 different diffeomorphism classes. These are 6 million different diffeomorphism classes of manifolds. All of them have they are all monotone, prequantizations with Chern class 0. But their contact Betti numbers, the rank of all their contact homology groups is the same for all of them. So the contact homology, at least on the nose, does not distinguish them. And they are, we don't have a complete theorem, but I will bet they are, the prequantizations are also 6 million different diffeomorphism classes. Okay? So here I explain a little bit the method that this double pyramid method that António Neves found to enumerate polytopes. I don't care about this. But I care more about, I care about this. Sorry. I'm not going to talk about this here because I think you guys don't care about this. I think you guys, I'm pretty sure you guys don't care about this. It's not I think. But I just wanted to, yeah, okay. Anyway, you see, this has more than meets the eye because I think, for me at least, these guys enumerated the number of cohomology rings, different ring structures on that cohomology. Those guys enumerated the number of diffeomorphism classes of cohomology rings for Bott manifolds. António Neves enumerated the number of toric diagrams RR equivalent to a particular one. These are 2 different worlds. Okay? He is not looking at invariants of cohomology rings. So these guys, for example, are looking how many elements in the cohomology ring do you have with square 0. That's one of the invariants. Okay. Nothing here. Here he's looking at how do you construct, how many inequivalent classes do you do from the construction you found. But the numbers are the same because they are doing different ways of enumerating the same class. Anyway, so here I think are two interesting questions that I leave at the end that come from this thing, I think. I think it's interesting to find out which toric diagrams are error determined, meaning which toric diagrams are unique with that particular error polynomial. For example, the simplex, which is the toric diagram of the standard contact structure on the odd-dimensional sphere, is error determined because it's just too small. The simplex, you see, toric diagrams have to be, the facets have to be integral simplices and so forth. There is no other thing. Okay? The simplex is error determined. So there is no other toric contact manifold that has the same contact Betti numbers as the sphere. There is another one that we know is error determined, which is the unit square. So the unit square, you see, when you prequantize S2 cross S2 with omega is equal to C1, you get, so when omega is equal to C1, you get what I wrote, the cube like this. Sorry, yeah. Sorry, no, not the cube like this. Stupid. You get the cross polytope, so the dual thing, the toric diagram is this guy. That was the, so you prequantize P1 cross P1 with this cohomology class, and you get this toric diagram. If you do the simply connected thing, which is when omega is 1, you are prequantizing S2 cross S2 with this moment polytope, and the toric diagram is it's not the dual because we have to do something, but it's the cube. It's combinatorial equivalent to this one, but it's smaller. There is no integral point inside. It's different common. Okay, it's small. So the cube. Okay. So, and this guy is also, you can, even by enumeration, you can see that the error polynomial of this guy is unique. Although this guy has another toric diagram, which I drew for the first Hilsbrook surface, which is error equivalent to this one has none. It's also error determined. And we believe that the higher dimension generalization of this unit square, which is not a cube because that's not a toric diagram, it's a dual, but it's which we call small cross polytopes, which are the toric diagrams of the prequantizations of the simply connected situation. You take S2 cross S2 cross S2, but the symplectic form is integral, but it's C1 over 2. Because C1 of the sphere is 2, so you can divide by 2 and get an integral class. These guys, we believe they are also error determined. There are no other toric symplectic manifolds with that thing, but we don't have a proof for that in general. Now, another question that I leave now, and this is a little bit of science fiction, but I like it. Leonardo doesn't like it so much, I think. So if Leonardo was giving this talk, he was not going to ask this question. But I like this question, which is the following. So we have these 6 million examples of toric diagrams in n equals 15. So this means that contact manifolds of dimension 31. Right? 2 times 15 plus 1, dimension 31. 6 million of them. All of them have the same contact Betti numbers. So you can find Reb vectors so that if you look at the flow, you have a fixed number of, I can tell you what is the number, but I don't remember now. I have it's something that depends on n. 2n, I think it's 15, n is 15, 30. They have 30 geometrically distinct closed orbits, Rib orbits. And then you compute the indices. They all, you cannot distinguish these manifolds, right? You have the same number of orbits with rank 2, 4, 6, so forth. And my question is, you can also look at the periods of these orbits. That's also something that you can compute. We are not using for anything. So the action, right? You can use the action of these orbits. You know everything about this. And it also has a combinatorial interesting description in terms of the polytopes, depending on the Reb vector that you do. And my question is this, so could we, instead of just looking at indices, if you look at indices and periods, and maybe look for all toric Reb vectors that you can put, non-degenerate ones, and look at that, can we distinguish these toric contact manifolds? Okay? That's my question. Because hearing for me means I have all the information in terms of number of periodic orbits, indices of periodic orbits, and periods of these orbits. And there are finitely many of them, and I know all its iterates, I know everything about this. If I only look at indices, I cannot distinguish these 6 minimum. I cannot distinguish any 2 of them. Nothing. What kind of information that does not go to, I don't know, maybe there is some full contact homology algebra with you count holomorphic curves with buildings, things like that. That's not for me. Okay, maybe there is. Maybe some of you know something that I don't know. I cannot compute that. But all these guys have even degree. The boundary map, cylindrical map is 0. So what? Is there something or pretty simple, or simply we cannot hear them? Hearing mean periods and indices. So it's even interesting in dimension in the first case, S2 cross S2 in the first Giesebrecht surface. You can compute everything there. Is there a way of distinguishing them? For that case, I know a particular way. I know, but I don't think if you look at the minimal period that you can get through all group vectors, it's different in one case and the other. But I don't know if that generalizes. Anyway, so here is the question. Thank you very much. Sorry for going over time.